Hello and welcome to our journey through one of the most catastrophic scenarios in modern astronomy. Tonight, we are not just talking about another asteroid or comet, but a phenomenon that could rewrite everything we thought we knew about planetary survival in our solar system. Something ancient and extraordinary is hurtling directly toward the red planet, a true interstellar wanderer, arriving after billions of years alone in the vast darkness between the stars, now on a collision course with Mars. This visitor, dubbed 3I Atlas, is not merely passing by our solar system. Unlike anything born in our cosmic neighborhood, 3I Atlas is a messenger from the depths of space, its origins shrouded in mysteries older than our own planet, and tomorrow it might deliver the most violent message our solar system has received in millions of years. What makes this potential cosmic collision even more astonishing isn't just the visitor's journey across unimaginable distances, but the catastrophic transformation it could unleash on Mars, a planetary scale event that could change the face of our neighboring world forever. Before we explore this apocalyptic scenario, imagine where you are right now, in a quiet room, perhaps comfortable and safe, unaware that tomorrow, millions of miles away, an enormous force could be reshaping an entire planet before our very eyes. If stories like this compel your imagination, consider subscribing or liking this program. It helps more curious minds connect and prepares us all to face the astonishing and sometimes terrifying possibilities that space throws at us. Now, take a moment. Let your mind expand and prepare to grasp what it truly means when cosmic forces collide, when an interstellar object like 3I Atlas, traveling at impossible speeds, meets the solid reality of a planet like Mars. This is the beginning of a story where the universe itself becomes the ultimate destroyer and creator, and we must confront what such a collision could mean, not just for Mars, but for our understanding of planetary survival in a universe full of wandering threats. But first, let's address the fundamental question that makes this scenario so mind-bending. What are the odds that an interstellar wanderer, traveling for billions of years through the void between stars, would arrive at our solar system tomorrow and strike Mars with perfect precision? The mathematical answer would require numbers so small they barely exist in human language. We would need to write decimal points, followed by more zeros than there are atoms in a grain of sand before reaching any meaningful digit. Yet this impossibility serves as our doorway into understanding something far more probable and profound. While 3I/Atlas will not collide with Mars tomorrow, the physics of such an event reveal truths about planetary vulnerability, cosmic violence, and the forces that have shaped worlds since the dawn of the solar system. Every planet bears scars from these encounters. Mars itself tells a story written in craters, carved by impacts that have pummeled its surface for 4.5 billion years. The object we call 3I/Atlas represents something extraordinary in our cosmic neighborhood. Unlike comets born in the outer reaches of our own solar system, this visitor carries the signature of deep space. Its trajectory follows what astronomers term a hyperbolic orbit, meaning it will never return to our vicinity. Once it completes its brief passage through our solar system, 3I/Atlas will continue its journey into the infinite darkness between stars, carrying with it whatever secrets it holds about the galaxy beyond. To understand what would happen if such an object struck Mars, we must first examine the nature of the wanderer itself. Current observations suggest 3 Hypothetical spans roughly 20 kilometers across, making it comparable in size to some of Earth's larger cities. But size alone tells only part of the story. This interstellar traveler moves with velocity that dwarfs anything native to our solar system. When astronomers track objects within our solar system, they measure speeds in terms of kilometers per second. A typical asteroid might travel at 15 to 20 kilometers per second relative to the Sun. Earth orbits our star at approximately 30 kilometers per second. These represent the baseline speeds for objects bound by solar gravity, following elliptical paths that have remained stable for eons. 3I/ATLAS moves differently. Its hyperbolic trajectory carries it at roughly 58 kilometers per second relative to the Sun as it approaches the inner solar system. This speed reflects its interstellar origin, accumulated through gravitational interactions with distant stars and the complex dynamics of galactic rotation. Such velocity speaks to journeys measured not in years or centuries, but in geological epochs spanning billions of revolutions around the galactic center. Mars orbits the Sun at an average distance of 228 million kilometers, completing one circuit every 687 Earth days. The red planet follows an elliptical path that brings it as close as 207 million kilometers to our star and carries it as far as 249 million kilometers away. These orbital mechanics create a complex dance between Mars and any approaching object. For our hypothetical collision to occur tomorrow, 3I/ATLAS would need to arrive at precisely the right location in space, at precisely the moment Mars occupies that same region. The probability calculations become staggering when we consider the three-dimensional nature of orbital mechanics. Mars presents a target roughly 6,700 kilometers in diameter, moving through space along a path that spans billions of cubic kilometers of volume. The mathematics of celestial mechanics reveal why such coincidences remain vanishingly rare. An object approaching from interstellar space encounters a solar system where planets occupy tiny fractions of the available volume. Even Jupiter, with its massive gravitational influence and enormous diameter, presents a target that covers less than 1/1,000,000th of its orbital path's cross-sectional area. But mathematical improbability should not diminish our curiosity about the physics involved. Throughout the history of the solar system, impacts have shaped planetary evolution in fundamental ways. The Moon's formation likely resulted from a Mars-sized object colliding with the early Earth. The asteroid that ended the dinosaurs' reign demonstrated how cosmic impacts can redirect the entire course of biological evolution. Venus may owe its backward rotation to an ancient collision that literally turned the planet upside down. Mars itself preserves evidence of countless impacts spanning its geological history. The Hellas Basin, stretching more than 2,000 kilometers across, marks the location where an asteroid or comet struck the planet with tremendous force billions of years ago. The northern hemisphere's dramatic difference in elevation compared to the southern highlands may reflect an even more massive impact that reshaped half the planet's surface. These ancient scars remind us that while tomorrow's collision with 3A/ATLAS remains impossible, similar events have occurred throughout cosmic history. The difference lies not in whether such impacts happen, but in their timing, location, and the specific characteristics of the impacting object. Every impact tells a unique story determined by velocity, angle, composition, and the geological state of the target world at the moment of collision. Understanding impact physics requires us to consider energy scales that challenge human comprehension. When we calculate the kinetic energy of a 20-kilometer object traveling at 58 kilometers per second, we encounter numbers that exceed the total energy output of human civilization across its entire history. Such calculations help us appreciate why impacts have served as primary agents of planetary change throughout the solar system's evolution. The thought experiment of tomorrow's impossible collision serves multiple purposes in our understanding of planetary science. It forces us to consider the fundamental physics governing high-velocity impacts. It reveals the vulnerability of planetary atmospheres to sudden, massive disruption. It demonstrates how single events can trigger cascades of change that persist for thousands or millions of years. Moreover, contemplating such scenarios helps us appreciate the cosmic context of planetary existence. Worlds do not evolve in isolation, but as part of a dynamic system where gravitational interactions, orbital resonances, and occasional violent encounters shape their long-term development. The apparent stability of planetary orbits masks an underlying reality of constant change occurring across timescales that dwarf human experience. As we prepare to explore what would unfold in our imaginary collision, we carry with us an understanding that while the specific scenario remains impossible, the physics we will examine operate continuously throughout the universe. Somewhere in the cosmos, similar collisions occur with regularity. The insights we gain from our thought experiment illuminate processes that have shaped not only our own solar system, but countless others across the galaxy. The cosmic dice continue to roll across space and time, occasionally producing combinations that redirect the fate of entire worlds. Tomorrow's collision with Mars will not occur, but the universe's capacity for such dramatic interventions remains constant, reminding us that planetary existence balances precariously between cosmic order and cosmic chaos. In examining this impossible scenario, we glimpse the violent artistry through which gravity, velocity, and matter collaborate to sculpt the landscapes of worlds. The story we are about to unfold speaks not only to Mars's potential fate, but to the fundamental processes that govern planetary evolution throughout the cosmos. 24 hours from now, according to our impossible scenario, a mountain-sized chunk of ancient ice and rock will pierce Mars's atmosphere at a speed that makes bullets seem motionless. The fundamental forces unleashed in this collision would redefine our understanding of planetary catastrophe. Energy represents the heart of this cosmic violence. When we multiply the mass of our 20-kilometer wanderer by half the square of its velocity, the resulting number staggers the imagination. A conservative estimate places 3I/Atlas at roughly 10 trillion kilograms, though the actual figure could range significantly higher depending on its density and internal structure. Moving at 58,000 meters per second, this interstellar messenger carries kinetic energy equivalent to approximately 17,000 trillion joules. To put this in perspective, imagine detonating every nuclear weapon ever built by humanity simultaneously, then repeating that explosion several thousand times over. The total energy release would approach 100 million megatons of TNT, dwarfing even the most powerful thermonuclear devices ever tested. But raw energy alone cannot capture the full complexity of what transpires when such forces meet planetary matter. The physics of hypervelocity impacts operate in realms where normal materials behave like fluids, where rock becomes plasma, and where the distinction between solid and liquid ceases to have meaning. As 3I/Atlas enters Mars's thin atmosphere, friction begins its work immediately. The interstellar visitor encounters atmospheric molecules at such tremendous speed that compression waves form ahead of the approaching body. These waves heat the surrounding air to thousands of degrees, creating a bow shock that announces the incoming catastrophe with brilliant luminosity. Mars' atmosphere, composed primarily of carbon dioxide with traces of nitrogen and argon, begins to glow like a neon sign as superheated gas molecules emit radiation across the electromagnetic spectrum. From orbit, the approaching impact would appear as a blazing star crossing the Martian sky, growing brighter with each passing second. The atmospheric entry phase lasts mere moments, unlike meteoroids that spend minutes crossing Earth's thicker atmosphere. 3I/Atlas would traverse Mars's atmospheric envelope in less than 10 seconds. During this brief interval, the outer layers of the impactor begin to ablate, shedding material that adds to the growing fireball surrounding the object's leading edge. Surface contact marks the transition from atmospheric phenomenon to geological catastrophe. The instant 3I/Atlas touches the Martian surface, both the impactor and the target rock begin to experience pressures exceeding 1 million Earth atmospheres. Under such conditions, the normal properties of matter dissolve into a realm governed by shock physics. The initial contact point experiences pressures so extreme that electrons are stripped from atomic nuclei, creating a brief state resembling the interior of a star. Temperature spikes to hundreds of thousands of degrees, hot enough to fuse silicate minerals into exotic forms that exist nowhere else in the solar system under natural conditions. A hemispherical shock wave radiates outward from the point of impact at speeds approaching 10 kilometers per second. This compression wave travels through solid rock as easily as sound travels through air, carrying pressures sufficient to instantly vaporize any material in its path. The shock front excavates a crater by literally blasting Martian bedrock into plasma and gas. During the first few seconds after impact, the growing cavity expands according to the cube root of time multiplied by energy. The excavation process follows precise mathematical relationships that govern crater formation across the solar system, from microscopic pits on spacecraft windows to basins hundreds of kilometers wide on planetary surfaces. The transient crater reaches its maximum diameter within minutes of impact. For an object the size of 3I/Atlas striking Mars at interstellar speeds, preliminary calculations suggest a transient crater diameter approaching 400 kilometers. This cavity would extend deep into the Martian crust, potentially penetrating through the planet's basaltic surface rocks into the underlying mantle. But the excavation phase represents only the beginning of crater formation. As the shock waves dissipate and the initial violence subsides, gravitational forces reassert their influence over the disrupted landscape. The crater walls, destabilized by the massive excavation, begin to collapse inward under their own weight. This gravitational collapse creates what planetary scientists call a complex crater structure. The central portion of the floor rebounds upward, forming a peak ring or central mountain as compressed material springs back like a slow-motion liquid drop. Meanwhile, the outer rim collapses in a series of terraced steps, creating the characteristic multi-ring structure observed in large impact basins throughout the solar system. The final crater diameter would likely exceed 600 kilometers, making it one of the largest impact features on Mars. Only the ancient Hellas Basin, formed billions of years ago during the solar system's violent youth, would rival this hypothetical scar in size and complexity. The excavation process launches enormous quantities of Martian material into ballistic trajectories close to the impact site. House-sized blocks of bedrock follow parabolic paths that carry them hundreds of kilometers from ground zero. Smaller debris travels even farther, with some particles achieving sufficient velocity to escape Mars's gravitational pull entirely. The mathematics of ejecta distribution follow well-established scaling laws that relate particle size to travel distance. The largest blocks concentrate within a few crater diameters of the rim, while progressively smaller fragments spread across greater distances. The finest dust particles, accelerated to speeds approaching Mars's escape velocity, begin their journey toward becoming interplanetary debris. Secondary craters begin forming across the Martian landscape as the heaviest ejecta blocks complete their ballistic flights. These secondary impacts, while individually smaller than the primary event, collectively modify vast areas of the planet's surface. Chains of aligned craters mark the trajectories of particularly large fragments, creating radial patterns that extend for thousands of kilometers from the main impact site. The excavation also exposes deep crustal materials that have remained hidden since Mars's formation 4.5 billion years ago. Ancient rock formations, preserved beneath layers of more recent deposits, suddenly find themselves scattered across the surface in a geological revolution compressed into minutes. Heat, generated by the impact, begins to alter the Martian surface in profound ways. The tremendous temperatures created during excavation vaporize not only the impactor, but also substantial volumes of target rock. This vapor expands rapidly, creating a debris plume that rises high above the Martian surface like a nuclear mushroom cloud scaled to planetary proportions. The ascending plume carries a mixture of vaporized impactor material and Martian rock, along with larger solid fragments that follow ballistic trajectories. This rising column of superheated debris becomes visible from orbit as a towering monument to cosmic violence, reaching altitudes comparable to the entire thickness of Mars's atmosphere. As the immediate violence of excavation subsides, the crater begins its long transformation from a raw wound in the planetary surface to a permanent geological feature. The process of relaxation and modification will continue for millions of years, but the basic structure established in those first few minutes will endure as long as Mars itself exists. The scale of destruction extends far beyond the immediate crater vicinity. Seismic waves generated by the impact propagate through Mars's interior, carrying news of the catastrophe to every corner of the planet. These planetary vibrations will trigger landslides, destabilize cliff faces, and potentially reactivate dormant geological faults across the entire Martian surface. In creating this enormous crater, the impact will have accomplished in moments what normally requires millions of years of geological processes. The excavation exposes a cross-section through Mars's crust, creating a natural laboratory for understanding the planet's internal structure and composition. Future explorers would find in this crater a window into the deep history of Mars, written in the rocks blasted up from far beneath the surface. Compare the thickness of a sheet of paper to the height of a mountain, and you begin to appreciate the scale difference between Mars's atmosphere and our own. Mars wraps itself in a gaseous envelope, so delicate that a human could walk through its thickest layers without difficulty. Yet this fragile shell becomes the stage for extraordinary transformation when cosmic forces intervene. The red planet's atmospheric blanket extends roughly 120 kilometers above its surface, though most of its mass concentrates within the lowest 20 kilometers. This wispy veil contains less than 1% of the pressure we experience on Earth, creating an environment so rarefied that liquid water cannot exist stably anywhere on the planet's surface under current conditions. But when our hypothetical interstellar visitor begins its final descent, this tenuous shroud suddenly awakens from 4 billion years of quiet stability. The approaching 20-kilometer wanderer compresses atmospheric molecules ahead of its path, creating a bow wave that propagates outward at supersonic velocities. The leading edge of this disturbance heats the surrounding carbon dioxide to incandescent brilliance. Within seconds of atmospheric entry, the chemistry of Mars begins to shift in ways not seen since the planet's turbulent youth. The superheated bow shock dissociates carbon dioxide molecules, breaking apart the stable compounds that have dominated the Martian atmosphere for eons. Oxygen atoms, liberated from their chemical bonds, find themselves free to participate in reactions impossible under normal Martian conditions. The energy deposited by atmospheric friction creates a temporary furnace in the upper atmosphere. Temperatures soar to levels that would vaporize most materials found on planetary surfaces. At these extreme thermal conditions, atmospheric chemistry operates according to rules that govern stellar interiors rather than planetary envelopes. As the interstellar object descends through increasingly dense atmospheric layers, the bow shock grows more pronounced. The compressed air ahead of the visitor begins to emit light across the electromagnetic spectrum, from radio waves through visible illumination to hard ultraviolet radiation. This expanding sphere of luminous gas creates an artificial aurora that outshines any natural phenomenon in Mars's recent history. The thermal energy released during atmospheric passage exceeds the planet's annual solar input within moments. This sudden influx of heat begins to drive convective processes that have remained dormant for billions of years. Rising columns of superheated gas create vertical circulation patterns that dwarf the largest dust storms in Martian recorded history. Atmospheric expansion becomes inevitable as temperatures climb far beyond anything the thin Martian envelope has experienced in geological ages. The heated gas begins to rise and spread, temporarily thickening the atmosphere to levels not seen since Mars possessed a denser, more Earth-like atmospheric composition in its distant past. The bow shock also generates acoustic phenomena that propagate through the atmospheric medium at the speed of sound. These pressure waves, while far more subtle than the electromagnetic effects, create planet-wide acoustic disturbances that could potentially trigger atmospheric instabilities across Mars' entire surface. Chemical reactions accelerate dramatically in the superheated environment created by atmospheric entry. Trace compounds normally locked in frozen stability begin to participate in complex molecular exchanges. Water vapor, previously confined to tiny concentrations in the coldest atmospheric layers, begins to sublime from polar ice deposits as global temperatures rise. The ascending thermal plume, created by atmospheric heating, reaches altitudes that extend beyond Mars's normal atmospheric boundaries. This rising column of hot gas temporarily extends the planet's atmospheric envelope, creating a transient expansion that increases atmospheric density at all altitudes. Electromagnetic effects accompany the thermal phenomena as ionized particles in the superheated atmosphere begin to interact with Mars's weak magnetic field remnants. These interactions generate radio emissions detectable across the solar system, announcing the atmospheric transformation to any observers equipped with appropriate instruments. The normally transparent Martian atmosphere becomes opaque as particulate matter from the ablating visitor mixes with native atmospheric components. This temporary opacity creates greenhouse effects that trap solar radiation more efficiently than the atmosphere has managed in billions of years. Pressure waves generated by the atmospheric heating propagate horizontally as well as vertically. These waves create temporary high pressure zones that migrate across the planet's surface at speeds approaching the velocity of sound in the Martian atmosphere. Such pressure variations could trigger avalanches, dust storms, and other geological phenomena across vast regions of the planet. The thermal plume continues its ascent long after the visitor has departed the atmospheric realm and begun its final approach to the surface. This rising column of superheated gas carries with it chemical signatures of both the interstellar wanderer and the Martian atmosphere, creating a unique molecular mixture that bears witness to the encounter between cosmic visitor and planetary envelope. Convective cells begin forming in the heated atmosphere as temperature gradients drive large-scale circulation patterns. These cells transport energy from the initial heating zone to regions thousands of kilometers distant, spreading the thermal effects across much of the planet's atmospheric volume. The sudden atmospheric heating also affects the planet's water cycle in profound ways. Subsurface ice deposits begin to sublime more rapidly as ground temperatures rise in response to increased atmospheric heating. This additional water vapor enhances the greenhouse effect, creating a feedback loop that amplifies the atmospheric changes. Dust particles normally settled in the lower atmosphere begin to rise as enhanced convection carries them to higher altitudes. This vertical transport of particulate matter further modifies the atmosphere's optical properties, altering how it absorbs and reflects solar radiation. The atmospheric transformation creates temporary weather patterns unlike anything in Mars' recorded meteorological history. Wind speeds increase as pressure gradients drive air movement between heated and cooler regions. These enhanced atmospheric dynamics generate weather systems with intensities approaching those seen on planets with much thicker atmospheres. As the interstellar visitor approaches the moment of surface contact, the atmospheric changes reach their peak intensity. The entire Martian atmosphere has become a dynamic, active system, temporarily resembling the atmospheric conditions that existed when Mars was a young, warmer world with the potential to support liquid water on its surface. The awakened atmosphere begins to interact with surface features in ways that have remained dormant for geological ages. Enhanced wind patterns scour dust from ancient deposits, while increased atmospheric pressure allows for more efficient heat transfer between the atmosphere and planetary surface. Chemical species that have remained trace constituents for billions of years suddenly become significant atmospheric components. The altered atmospheric chemistry creates conditions that could potentially support chemical reactions impossible under normal Martian atmospheric conditions. The atmospheric awakening represents a temporary return to a more dynamic planetary state, offering a glimpse of what Mars might have been like during its more geologically active past. This transformation demonstrates the delicate balance that maintains planetary atmospheric systems and reveals how external forces can dramatically alter these equilibrium states. Even as the visitor approaches its final moments before surface contact, the atmospheric changes continue to propagate outward, spreading the effects of this cosmic encounter across the entire planetary envelope. The awakened atmosphere serves as both herald and participant in the planetary transformation about to unfold. Observe how a single raindrop striking still water creates expanding rings that reshape the entire pond's surface, and you glimpse a gentler version of what unfolds when cosmic forces sculpt planetary landscapes. The excavation about to begin will carve a wound in Mars so profound that it rewrites the geography of an entire hemisphere in the span of minutes. The moment of contact between visitor and planet marks the beginning of the most rapid geological transformation in Mars's 4 billion year history. Where once the northern plains stretched in gentle undulations toward distant horizons, a cavity begins to form that will eventually span distances comparable to the width of France. Initial excavation proceeds according to the cube root scaling laws that govern crater formation throughout the solar system. Each second that passes sees the growing cavity expand outward and downward, following mathematical relationships as precise as those governing planetary orbits. The excavation front advances at velocities measured in kilometers per second, faster than sound travels through solid rock. The transient cavity grows through a process that combines vaporization, melting, and mechanical disruption of target materials. Near the point of initial contact, temperatures and pressures create conditions found nowhere else in the solar system under natural circumstances. Rock becomes plasma, then reconstitutes into forms unknown in terrestrial geology. As excavation continues, the advancing cavity wall encounters different geological layers that tell the story of Mars's formation and evolution. The impact site, located in the northern lowlands, initially penetrates relatively young lava flows that solidified billions of years ago when Mars still possessed active volcanism. Deeper excavation reveals progressively older materials, creating a reverse archaeological dig that exposes rocks formed during Mars's earliest epochs. Ancient impact breccias compressed and heated by countless smaller collisions over geological time suddenly find themselves excavated and scattered across the expanding crater rim. The excavation process launches Martian bedrock along ballistic trajectories that follow precise parabolic paths determined by launch angle and velocity. The largest blocks, some comparable in size to city buildings, travel distances measured in hundreds of kilometers before returning to impact the surface as secondary projectiles. Smaller fragments achieve higher velocities due to their reduced air resistance during the brief atmospheric passage. These particles spread across much greater distances, creating a continuous ejecta blanket that gradually thins with distance from the primary excavation site. The finest particles approach Mars's escape velocity beginning their journey to become interplanetary dust. The mathematical relationship between particle size and travel distance creates a natural sorting mechanism. Close to the crater rim, house-sized boulders accumulate in chaotic piles. At intermediate distances, car-sized fragments dominate the debris field. Farther away, pebble-sized material creates a relatively smooth ejecta layer. The excavation reaches its maximum extent within 10 minutes of initial contact, creating a transient cavity approximately 400 kilometers in diameter. This temporary crater extends deep into the Martian crust, potentially reaching the boundary between surface basalts and the deeper, more primitive crustal materials. But the transient cavity represents only the beginning of crater formation. The laws of gravity, temporarily overwhelmed by the violence of excavation, begin to reassert their influence over the disrupted landscape. The steep walls of the initial cavity cannot maintain their slopes against gravitational forces. Gravitational collapse begins almost immediately as the transient cavity walls start their inward migration. This collapse occurs in stages, with the deepest portions responding first to gravitational instability. The central floor begins to rebound upward as compressed crustal materials spring back like a slow-motion liquid drop. The central uplift grows into a mountainous peak ring that rises several kilometers above the surrounding crater floor. This uplift brings deep crustal materials to the surface, exposing rocks that formed during Mars' earliest geological periods. Future geological surveys would find in this central peak a complete cross-section through billions of years of Martian crustal evolution. Simultaneously, the crater rim begins its collapse through a series of terraced steps. Each terrace represents a gravitational failure zone where the steep crater walls cannot maintain their structural integrity. These terraced walls create the characteristic appearance of complex craters observed throughout the solar system. The final crater structure settles into a multi-ring basin with a diameter exceeding 600 kilometers. The outermost ring marks the limit of major structural deformation, while inner rings reflect the complex interplay between excavation dynamics and gravitational collapse. Secondary crater formation begins across the Martian landscape as ejecta blocks complete their ballistic flights. Chains of aligned craters mark the trajectories of fragment clusters launched from specific sectors of the primary excavation. These secondary craters create their own smaller ejecta blankets, further modifying the surrounding terrain. The largest secondary craters, formed by multi-kilometer fragments, create their own complex structures with central peaks and terraced walls. These secondary features add to the overall modification of the Martian landscape, extending the geological transformation far beyond the primary crater's immediate vicinity. The excavation exposes a vertical cross-section through Mars's crustal history that would normally require drilling kilometers below the surface to examine. Ancient impact melts, crystallized lava flows, and sedimentary deposits suddenly become accessible at the surface level throughout the crater's interior. Thermal effects from the excavation begin to alter the exposed materials through a process called shock metamorphism. The extreme pressures and temperatures generated during crater formation create new mineral phases that serve as permanent markers of the event. These shock metamorphosed materials would provide future investigators with precise indicators of the pressures and temperatures achieved during excavation. The crater's formation also creates a natural laboratory for studying Mars' internal structure. The central peak ring exposes mantle materials that have never before appeared at the Martian surface. These deep crustal samples offer insights into the planet's formation, differentiation, and thermal evolution. Heat generated during excavation begins to melt substantial volumes of subsurface ice deposits. This melting creates temporary lakes within the crater structure, marking the first appearance of liquid water on Mars's surface in perhaps billions of years. These ephemeral bodies of water begin their own geological processes of erosion and deposition. The crater structure influences local atmospheric dynamics by creating a topographic depression that alters wind patterns across the region. Air circulation within the crater basin creates unique microclimate conditions that persist long after the initial formation event. Gravitational anomalies created by the mass redistribution during excavation generate subtle but measurable changes in Mars' gravitational field. These anomalies would remain detectable by sensitive instruments for millions of years, serving as permanent signatures of the excavation event. The newly formed crater begins its long evolution from a fresh scar to an integrated part of the Martian landscape. Wind-blown sediments start to accumulate on the crater floor, while thermal cycling begins the slow process of erosion that will gradually modify the sharp crater features over geological time. The crater that rewrites Mars's northern hemisphere geography represents more than just a hole in the ground. It creates a permanent feature that influences atmospheric circulation, geological processes, and the planet's overall thermal balance. This single excavation transforms Mars from a world with subtle topographic variations to one dominated by one of the largest crater structures in the solar system. The geographic transformation extends beyond the crater itself through the modification of regional drainage patterns, atmospheric circulation, and thermal regulation. The presence of such a large topographic feature influences weather patterns, dust transport, and potentially even the planet's rotational dynamics through the redistribution of mass. In carving this enormous crater, the excavation process creates a landmark visible from orbit around any planet in the solar system. The geographic transformation marks Mars permanently, creating a feature that will endure long after all traces of current Martian surface processes have been erased by time. Mars trembles in the pre-dawn darkness of Sol, 47,829, unaware that in moments it will experience the most violent planetary convulsion in its recorded geological history. The red planet's interior, dormant for billions of years, prepares to conduct a symphony of seismic energy that will reverberate through every layer of its internal structure. The initial shock wave radiates outward from the point of contact at velocities that exceed the speed of sound in solid rock by factors of 3 or 4. This primary compression wave, traveling at approximately 15 kilometers per second through the Martian crust, carries pressure signatures of the surface excavation deep into the planet's interior. Mars' internal architecture becomes a complex medium through which seismic energy propagates according to the varying densities and compositions of different geological layers. The basaltic surface rocks, iron-rich core, and intermediate mantle materials each conduct seismic waves at different velocities, creating a natural seismograph that records the event's magnitude throughout the planetary interior. The primary pressure wave reaches the planet's opposite hemisphere within 20 minutes, having traveled through more than 6,000 kilometers of Martian interior. At the antipodal point, approximately 12,000 kilometers from the excavation site, the converging seismic energy creates focused ground motion that rivals the intensity experienced near the original excavation. Secondary seismic waves, traveling more slowly through the planetary interior, carry different components of the initial disturbance. These shear waves cannot propagate through liquid materials, providing natural probes that reveal the physical state of Mars' deep interior. The wave patterns generated by the excavation offer unprecedented insights into the planet's internal structure. The seismic energy propagation creates standing wave patterns within the Martian interior that cause the entire planet to vibrate like a struck bell. These planetary oscillations, known as normal modes, continue for hours after the initial disturbance, causing measurable ground motion across the entire planetary surface. Mars' partially molten core responds to the seismic disturbance by generating secondary pressure waves that reflect and refract at the core mantle boundary. These deep interior waves carry energy back toward the surface, creating additional ground motion that arrives minutes or hours after the primary disturbance. The northern and southern polar ice caps experience particularly dramatic effects as seismic waves interact with the frozen carbon dioxide and water ice deposits. The mechanical properties of ice differ substantially from those of solid rock, causing seismic waves to reflect, refract, and attenuate in complex patterns as they encounter these polar deposits. Thermal expansion effects accompany the seismic disturbance as mechanical energy converts to heat within the planetary interior. Although the total thermal energy added to Mars's interior represents a tiny fraction of the planet's thermal budget, local heating effects along seismic wave paths create measurable temperature increases in crustal materials. The seismic disturbance triggers avalanches and landslides across Mars's most geologically unstable regions. The towering cliffs of Valles Marineris, the solar system's largest canyon system, experience massive slope failures as seismic shaking destabilizes rock formations that have balanced precariously for millions of years. Olympus Mons, the solar system's largest volcano, responds to the planetary shaking through subtle but measurable deformation. The enormous mass of this volcanic structure creates local gravitational anomalies that focus seismic energy, potentially triggering small-scale geological adjustments within the volcanic edifice. Subsurface ice deposits throughout Mars's middle latitudes begin to sublime more rapidly as mechanical energy from seismic waves converts to heat. This enhanced sublimation releases water vapor into the atmosphere, contributing to the ongoing atmospheric transformation triggered by the excavation event. The seismic waves interact with Mars's ancient impact crater structures in complex ways that reveal the internal architecture of these geological features. Seismic energy reflects from the boundaries between crater fill materials and surrounding bedrock, creating distinctive wave patterns that illuminate the three-dimensional structure of ancient excavations. Fault systems throughout the Martian crust respond to the seismic disturbance through renewed geological activity. Ancient fracture networks, dormant for hundreds of millions of years, experience renewed stress as seismic waves alter the regional stress field throughout the planet's crustal layers. The seismic energy propagation triggers the release of trapped gases from subsurface geological formations. Carbon dioxide, water vapor, and other volatile compounds begin to outgas more rapidly as mechanical disturbance enhances permeability along fracture networks and geological contacts. Mars' weak magnetic field remnants interact with the moving crustal materials in subtle ways that create electromagnetic disturbances detectable by sensitive instruments. The motion of iron bearing minerals through these weak magnetic fields generates electrical currents that contribute to the planet's overall electromagnetic signature. The seismic disturbance affects the planet's rotational dynamics through the redistribution of angular momentum caused by internal mass movements. While these effects remain extremely small, they represent measurable changes in Mars' rotation rate and axial orientation that persist for extended periods. Groundwater systems within the Martian crust respond to the seismic shaking through changes in hydraulic pressure and permeability. Ancient aquifer systems, sealed for millions of years, potentially experience renewed fluid flow as seismic waves alter the stress state of subsurface rock formations. The propagating seismic waves create complex interference patterns where wave fronts from different propagation paths intersect. These interference zones generate areas of enhanced ground motion alternating with regions of relative seismic quiet, creating a complex mosaic of seismic effects across the planetary surface. Deep crustal materials respond to the seismic disturbance through brittle failure and ductile deformation, depending on temperature, pressure, and composition conditions at different depths. The transition zone between brittle and ductile behavior shifts temporarily as seismic heating alters the mechanical properties of crustal rocks. The seismic energy propagation through Mars' interior provides a natural seismic tomography experiment that reveals details of the planet's internal structure, previously accessible only through theoretical modeling. The wave patterns generated by the single event offer insights equivalent to decades of conventional seismological monitoring. Mars' internal heat flow responds to the seismic disturbance through enhanced conductive and convective heat transfer. The mechanical stirring effect of seismic waves temporarily increases the efficiency of heat transport through the planet's interior, potentially affecting long-term thermal evolution patterns. The seismic waves interact with subsurface void spaces, including lava tubes and natural caverns, creating resonance effects that amplify ground motion in specific frequency ranges. These amplification effects create unique seismic signatures that reveal the presence and characteristics of subsurface void networks. As the most intense seismic energy dissipates, Mars settles into a new equilibrium state, subtly different from its pre-event condition. The mechanical reorganization of crustal stress fields, enhanced permeability of fracture networks, and altered thermal gradients create lasting changes that influence geological processes for millions of years. The planetary percussion performance concludes with Mars forever changed at the deepest levels of its internal structure. The seismic symphony, conducted by cosmic forces and performed by planetary materials, leaves behind a world whose interior architecture bears permanent witness to this moment of geological transformation. The drums of Mars fall silent, but their reverberations continue to echo through crustal rocks and subsurface formations, carrying forward the mechanical memory of this encounter between planet and cosmos. The red planet's interior will never again be quite the same, having participated in a seismic event that reshaped its internal dynamics across all scales of geological organization. So, what forces could disturb the ancient orbital ballet that has kept Mars's two small moons circling their parent planet for billions of years? The excavation event about to unfold will subject Phobos and Deimos to gravitational stresses, debris bombardment, and orbital perturbations that threaten to end their cosmic dance forever. Phobos, the larger and closer of Mars's two natural satellites, orbits a mere 6,000 kilometers above the Martian surface. This proximity places the irregularly shaped moon well within the danger zone when debris from the excavation begins its ballistic journey outward from the planetary surface. The small moon, measuring only 27 kilometers across at its widest dimension, presents a vulnerable target for the countless fragments launched skyward by the excavation process. The gravitational relationship between Mars and its moons operates according to precise mathematical laws that have maintained orbital stability for eons. But the sudden redistribution of mass during crater formation creates temporary gravitational anomalies that propagate outward through the Martian gravitational field. These perturbations carry enough energy to alter the delicate orbital mechanics that govern moon planet interactions. Deimos, orbiting at a more distant 23,000 kilometers from Mars, initially appears safer from the immediate debris hazard. However, this outer moon's orbital period of 30 hours means it will complete more than half a revolution around Mars during the most intense phase of debris ejection. This orbital motion carries Deimos through multiple debris clouds as ejecta particles spread throughout the Mars orbital system. The mathematical relationship between orbital velocity and debris particle speed determines which fragments pose the greatest threat to the moons. Particles launched at velocities approaching Mars's escape speed travel fast enough to intercept even the swiftly moving Phobos, which completes an orbit in just 7.5 hours. Phobos experiences the first debris strikes within minutes of the excavation event. House-sized blocks, launched along ballistic trajectories that carry them far above Mars's surface, begin to intersect the moon's orbital path. The low gravitational field of the small satellite cannot capture these high-velocity projectiles, but direct strikes begin to crater Phobos's already heavily scarred surface. The largest debris fragments carry enough kinetic energy to excavate craters several kilometers across on Phobos's surface. Given that the moon measures only 27 kilometers in diameter, such excavations represent significant fractions of the satellite's total volume. Multiple large strikes could potentially shatter the small moon into fragments. Deimos faces a different but equally serious threat from the fine particulate matter that achieves the highest velocities during excavation. These dust-sized particles, accelerated to speeds approaching interplanetary velocities, create a diffuse cloud that gradually expands throughout the Mars orbital system. This particle cloud subjects both moons to enhanced micrometeorite bombardment for months following the excavation. The sudden change in Mars' gravitational field, caused by the excavation of billions of tons of material from the northern hemisphere, creates subtle but measurable alterations in the orbital mechanics of both moons. These gravitational perturbations manifest as small changes in orbital eccentricity, inclination, and semi-major axis that accumulate over multiple orbital periods. Tidal forces between Mars and its moons also respond to the gravitational field changes created by mass redistribution during excavation. The formation of the enormous crater creates a permanent gravitational anomaly that affects tidal stresses experienced by both satellites. For Phobos, already stressed by its close proximity to Mars, these additional tidal forces could trigger structural failure along existing fracture planes. The thermal environment around Mars changes dramatically as the excavation event heats the planetary surface and atmosphere. This enhanced thermal radiation affects both moons, though Phobos experiences more significant heating due to its closer orbital distance. The increased thermal input could begin to sublime volatile compounds trapped within the moon's regolith layers. Electromagnetic effects accompanying the excavation create charged particle environments that interact with both moons' surfaces. While neither Phobos nor Deimos possesses significant magnetic fields, their surfaces accumulate electrical charges through interactions with the enhanced particle flux generated by atmospheric heating and debris vaporization. The orbital resonances that help maintain long-term stability in the Mars satellite system face disruption from the gravitational perturbations caused by mass redistribution. These resonances, which have prevented orbital decay or ejection for billions of years, must re-establish themselves in response to the altered gravitational environment. Phobos' already precarious orbital stability faces additional challenges from the excavation effects. The Moon currently orbits below Mars's synchronous orbital radius, meaning tidal forces gradually spiral it inward toward the planet. The gravitational perturbations from excavation could accelerate this orbital decay, potentially reducing Phobos' remaining lifetime from tens of millions of years to much shorter timescales. The debris cloud surrounding Mars creates enhanced atmospheric drag effects that affect both Moon's orbital mechanics. While the primary atmospheric effects occur close to the planetary surface, the expanding debris cloud extends the effective atmospheric envelope to altitudes that intersect both satellite orbits. Secondary cratering events on both moons create their own small debris clouds that contribute to the overall disruption of the Mars orbital environment. These secondary particles, launched from moon surfaces at relatively low velocities, remain gravitationally bound to the satellite system and continue to interact with both moons for extended periods. The excavation event potentially triggers avalanches and slope failures on both moon surfaces as seismic waves from the main event propagate through the Mars gravitational field. While these seismic effects remain relatively weak at satellite orbital distances, they could destabilize loose material accumulated in crater rims and along fracture zones. Orbital tracking of both moons becomes complicated by the enhanced particle environment created by excavation debris. The dust clouds surrounding both satellites affect radar and optical observations, making precise orbital determination more difficult during the months following the excavation event. The long-term evolution of the Mars satellite system faces permanent alteration due to the excavation effects. The gravitational field changes, enhanced debris environment, and altered tidal stress patterns create new boundary conditions that will influence satellite orbital evolution for millions of years. Both moons begin to accumulate excavation debris on their surfaces, creating new geological features that mark this unique moment in the satellite system's history. The composition of this debris provides future investigators with samples of deep Martian crustal materials that would otherwise remain inaccessible for detailed study. The excavation event creates a natural experiment in satellite system dynamics that reveals fundamental principles governing moon-planet interactions. The response of Phobos and Deimos to the gravitational and mechanical perturbations offers insights into the stability and evolution of satellite systems throughout the solar system. As the most intense phase of debris ejection subsides, both moons settle into modified orbital configurations that reflect their encounter with cosmic violence. The ancient dance between Mars and its satellites continues, but with new choreography written by the gravitational and mechanical forces unleashed during the excavation event. The crisis faced by Mars' dancing moons demonstrates the interconnected nature of planetary systems, where single events can propagate effects throughout entire gravitational neighborhoods. The orbital ballet continues, forever changed by its encounter with the forces that reshape worlds and redirect the paths of their celestial companions. Mars launches its own material into space at velocities that transform planetary debris into interplanetary projectiles. The excavation process hurls millions of tons of Martian rock, ice, and dust along ballistic trajectories that carry fragments throughout the inner solar system and beyond. The mathematics governing ejecta distribution follows scaling relationships established through decades of crater research on planetary surfaces throughout the solar system. These equations predict how particle size relates to launch velocity, which determines the ultimate destination of each fragment blasted from the excavation site. The largest ejecta blocks, comparable in size to office buildings, achieve launch velocities of several kilometers per second. These substantial fragments follow parabolic paths that carry them hundreds of kilometers from the excavation before returning to strike the Martian surface as secondary projectiles. Their ballistic flights create chains of aligned craters that radiate outward from the primary excavation like spokes on a cosmic wheel. Intermediate-sized fragments, ranging from car-sized boulders down to basketball-sized rocks, achieve higher launch velocities due to their reduced atmospheric drag during the brief transit through Mars's thin atmosphere. These projectiles spread across much greater distances, creating a continuous ejecta blanket that gradually thins with increasing distance from the excavation rim. The smallest particles experience the least atmospheric deceleration and achieve the highest velocities relative to their size. Pebbles and sand grain-sized fragments approach Mars's escape velocity of 5 kilometers per second, beginning their transformation from planetary surface material into interplanetary debris. A significant fraction of the finest ejecta actually exceeds Mars's escape velocity, launching Martian material on trajectories that will carry it throughout the solar system. These escaped particles become part of the zodiacal dust cloud that permeates interplanetary space, carrying with them chemical signatures of the red planet's crustal composition. The temporal distribution of ejecta follows the excavation process, with the fastest moving particles departing during the earliest phases of crater formation. This temporal sequence creates a natural chronometer, with arrival times at various solar system destinations, encoding information about the excavation dynamics. Within hours of the excavation, the fastest ejecta particles begin their interplanetary journeys at speeds sufficient to reach Earth's orbital distance within several years. These high-velocity fragments carry with them samples of deep Martian crustal materials that would otherwise remain inaccessible to direct study. The ejecta cloud creates temporary debris rings around Mars as particles with velocities just below escape speed enter elliptical orbits around the planet. These ephemeral rings, composed of rocky debris, rather than ice particles, persist for months before orbital decay returns most fragments to the Martian surface. Gravitational interactions with Mars' moons further complicate ejecta trajectories, with some particles receiving gravitational assists that boost their velocities beyond escape speed. Phobos and Deimos act as inadvertent slingshots, redirecting debris flows and adding complexity to the overall ejecta distribution pattern. The chemical composition of ejecta varies with launch velocity and excavation depth, creating a natural sorting mechanism that segregates different crustal materials according to their ballistic destinations. Surface materials dominate the low-velocity ejecta that remains gravitationally bound to Mars, while deeper crustal samples concentrate among the high-velocity particles that achieve interplanetary trajectories. Atmospheric interactions during ejecta transit create luminous phenomena as high-velocity particles compress and heat the thin Martian atmosphere. The ejecta cloud generates its own aurora-like effects as particle streams interact with atmospheric molecules, creating a temporary light show visible across much of the Martian hemisphere. The thermal effects of atmospheric friction begin to modify ejecta particles during their ascent through Mars's atmosphere. Surface ablation removes the outermost layers of larger fragments, while smaller particles experience complete melting and solidification cycles that alter their internal structure and composition. Secondary fragmentation occurs as larger ejecta blocks experience thermal stress and mechanical shock during their ballistic flights. This fragmentation process creates cascading size distributions that multiply the number of individual particles while reducing their average dimensions. The ejecta storm affects spacecraft throughout the Mars orbital environment, creating hazardous debris fields that persist for extended periods. Satellites and orbiters face enhanced micrometeorite flux as the particle cloud gradually expands throughout the planet's gravitational sphere of influence. Some ejecta particles follow complex trajectories that carry them on multi-orbit paths around Mars before eventual surface impact. These extended trajectories create delayed secondary bombardment that continues for months after the primary excavation, gradually modifying surface features across broad regions of the planet. The momentum carried by escaping ejecta represents a measurable loss of angular momentum from the Mars system. While this effect remains extremely small, it contributes to subtle changes in the planet's rotational dynamics that accumulate over extended timescales. Magnetic field interactions affect the trajectories of iron-bearing ejecta particles as they move through the weak remnants of Mars' ancient magnetic field. These electromagnetic effects create slight trajectory modifications that influence the final distribution patterns of metallic debris components. The ejecta storm creates a natural meteor shower visible from Earth as high-velocity Martian particles eventually intersect our planet's orbital path. These Martian meteoroids, arriving years after the excavation event, provide terrestrial laboratories with fresh samples of red planet materials launched from unprecedented depths within the planetary crust. Solar radiation pressure begins to affect the smallest ejecta particles once they enter interplanetary space, gradually modifying their trajectories through photon momentum transfer. This radiation pressure creates size-dependent orbital evolution that further disperses the finest debris throughout the inner solar system. The excavation process also launches substantial quantities of water ice and frozen carbon dioxide from subsurface deposits. These volatile materials begin to sublime immediately upon exposure to solar radiation, creating transient cometary activity as Martian ice sublimates in the vacuum of space. Particle collisions within the dense ejecta cloud generate secondary fragmentation events that multiply the number of individual debris pieces while reducing their average size. These collision cascades contribute to the overall evolution of the particle size distribution as the ejecta storm expands outward from Mars. The chemical weathering history preserved in ejecta particles provides scientific information about Mars's atmospheric evolution and surface processes. Particles launched from different depths carry distinct chemical signatures that record billions of years of planetary environmental change. Gravitational focusing effects concentrate ejecta along specific trajectories determined by the relative positions of Mars and other planetary bodies at the time of excavation. These focusing mechanisms create enhanced particle densities along particular orbital paths that increase collision probabilities with other solar system objects. The ejecta storm establishes Mars as a temporary source of interplanetary debris, transforming the red planet from a passive recipient of cosmic bombardment into an active contributor to the solar system's population of small particles. This role reversal demonstrates how single catastrophic events can alter the dynamics of entire planetary systems. As the ejecta storm expands beyond Mars' gravitational influence, it carries with it a permanent record of this moment in planetary history. The scattered debris will continue to orbit the Sun for millions of years, serving as messengers that bear witness to the day when Mars briefly became a comet, launching its own material into the cosmic void. The storm of Martian ejecta represents more than just displaced planetary material. It embodies the transformation of a world from passive observer to active participant in the ongoing exchange of matter between planets that has shaped solar system evolution since its earliest epochs. 8 minutes after the excavation begins, light from the Martian catastrophe reaches Earth, carrying the first electromagnetic signatures of planetary transformation across 150 million kilometers of interplanetary space. Human observers, gathered around telescopes from professional observatories to amateur stargazers' backyards, witnessed the birth of an artificial star in the constellation Gemini. The initial optical flash appears as a point of light that rapidly brightens to rival Jupiter in apparent magnitude. Professional astronomers, tracking Mars through their instruments, observe the planet's familiar reddish disk suddenly develop a brilliant white spot that expands outward from the excavation site. The thermal radiation from superheated ejecta creates temperatures hot enough to emit visible light across the electromagnetic spectrum. Earth's atmospheric observing conditions affect how clearly ground-based observers can track the unfolding events. Atmospheric turbulence that normally limits telescopic resolution becomes irrelevant when observing phenomena bright enough to outshine the entire Martian disk. Even modest amateur telescopes reveal the expanding luminosity as it spreads across the planet's northern hemisphere. The Tebre excavation's electromagnetic signature extends far beyond visible light, creating radio emissions detectable by Earth's largest radio telescope arrays. These radio waves, generated by the ionization of atmospheric gases and the electromagnetic effects of high-velocity ejecta, provide additional channels for observing the planetary transformation from our distant vantage point. Infrared observations reveal the thermal evolution of the excavation site as temperatures gradually decrease from the initial peak values. Earth-based infrared telescopes track the cooling process over hours and days, watching as the thermal signature shifts from white-hot temperatures down through red-hot and eventually to merely warm compared to the surrounding Martian surface. Spectroscopic analysis of light from the excavation site reveals chemical signatures of vaporized Martian crustal materials. Earth-based spectrometers detect emission lines from silicon, iron, magnesium, and other elements that comprise Martian bedrock, providing direct chemical analysis of materials excavated from deep within the red planet's crust. The expanding ejecta plume becomes visible from Earth as a towering column of debris that extends high above the Martian surface. This debris column, backlit by thermal emission from the excavation site, creates a distinctive silhouette against the planet's disk that evolves over time as gravitational forces shape the ascending material. Atmospheric effects on Mars become observable from Earth through changes in the planet's overall brightness and color. The temporary thickening of the Martian atmosphere alters how sunlight reflects from the planetary surface, creating subtle but measurable changes in the planet's photometric properties as observed through Earth-based telescopes. The excavation triggers global dust storms on Mars that become visible from Earth within days of the initial event. These planet-wide dust clouds, stirred up by atmospheric heating and enhanced circulation patterns, gradually obscure surface features and alter Mars's appearance from a clearly defined disk to a more uniform hazy sphere. Amateur astronomers contribute valuable observations through coordinated observing campaigns that track the event's evolution across multiple nights. The distributed nature of Earth-based observing allows continuous monitoring as the planet's rotation carries different observatory sites into favorable viewing positions. Professional space agencies redirect Earth-orbiting telescopes to focus on Mars during the critical observation period. Space-based instruments, unaffected by atmospheric turbulence and absorption, provide high-resolution observations across wavelengths impossible to observe from Earth's surface. The excavation creates gravitational wave signatures detectable by Earth's most sensitive gravitational wave observatories. While these signals remain extremely weak, the sudden redistribution of mass during crater formation generates ripples in spacetime that propagate outward at light speed, reaching Earth's gravitational wave detectors within minutes of the excavation. Magnetic field measurements from Earth's magnetosphere show subtle responses to electromagnetic disturbances propagating from Mars. The planet's magnetic field sensors detect anomalous fluctuations that correlate with the timing of electromagnetic emissions from the excavation site. The event triggers enhanced meteor activity in Earth's atmosphere as high-velocity Martian ejecta begins its multi-year journey toward our planet. While the first Martian meteoroids will not arrive for several years, orbital calculations predict enhanced meteor shower activity that will persist for decades. Earth's atmospheric entry heating affects Martian meteoroids differently than typical solar system debris due to their unique composition and launch conditions. These particles carry chemical and isotopic signatures that distinguish them from asteroidal or cometary materials, providing laboratories with samples of Mars launched from unprecedented depths. Tidal measurements on Earth reveal infinitesimally small, but theoretically detectable changes in gravitational attraction as Mars's mass distribution shifts during excavation While these effects remain far below the threshold of practical measurement, they represent genuine physical interactions between the two planets. The excavation event influences Earth's atmospheric dynamics through subtle changes in solar radiation patterns. The enhanced reflectivity of Mars's temporarily thickened atmosphere alters the planet's contribution to zodiacal light, creating measurable changes in Earth's nighttime sky brightness. Radio telescopes on Earth detect communication disruptions from Mars orbiters and landers as the expanding debris cloud interferes with spacecraft operations. These communication blackouts provide indirect measurements of debris density and distribution around Mars. The event creates opportunities for citizen science projects as amateur observers contribute photographs, sketches, and photometric measurements of Mars' changing appearance. Social media platforms become repositories for observational data as astronomy enthusiasts share their documentation of the unfolding transformation. Earth's scientific satellites in solar orbit provide additional observing platforms with unique viewing geometries relative to Mars. These spacecraft offer perspectives unavailable from Earth's surface, revealing aspects of the excavation visible only from specific orbital positions in the inner solar system. The excavation influences Earth's astronomical community through the coordination of international observing campaigns. Professional and amateur observers collaborate to maintain continuous coverage of the event, creating a global network dedicated to documenting this unique moment in planetary science. Atmospheric scientists on Earth use the event as a natural laboratory for studying atmospheric dynamics under extreme conditions. The temporary transformation of Mars's atmosphere provides insights into atmospheric physics that inform understanding of atmospheric evolution on Earth and other planets. The event affects Earth's space situational awareness networks as tracking systems monitor the expanding debris cloud around Mars. These observations contribute to models of debris distribution that inform future mission planning for Mars exploration. Educational institutions worldwide incorporate observations of the event into astronomy curricula, providing students with real-time experience observing planetary transformation. The event becomes a teaching moment that demonstrates the dynamic nature of planetary systems. The excavation creates a permanent change in Mars's appearance from Earth, establishing a new baseline for telescopic observations. Future generations of astronomers will observe Mars with knowledge that its northern hemisphere bears the permanent scar of this cosmic encounter. As Earth continues its orbital journey, the planet carries with it human witnesses to a moment of planetary transformation. The observations gathered from our world provide a complete record of how cosmic forces can reshape entire planets within the span of hours, viewed from the unique perspective of another world in the same solar system. Earth's role as observer transforms our planet into a scientific instrument, its entire surface serving as a platform for documenting cosmic events. The alien skies above Mars, temporarily transformed by cosmic violence, remind us that planetary systems remain dynamic, ever-changing theaters where dramatic transformations can unfold on timescales measurable in human lifetimes. Notice how a single match can warm an entire room during a cold winter evening, and you begin to understand how atmospheric heating can temporarily transform an entire planet's climate system. The excavation event subjects Mars to thermal input equivalent to thousands of years of solar heating compressed into hours, creating conditions the red planet has not experienced since its geological youth. The fundamental mechanism driving this temporary climate transformation begins with the rapid heating of atmospheric gases through compression, friction, and thermal radiation from excavated materials. Mars's thin atmosphere, normally transparent to most solar radiation, suddenly becomes an efficient absorber of thermal energy across multiple wavelengths. Carbon dioxide, the primary constituent of Mars's atmosphere, responds to increased temperatures by expanding according to ideal gas law relationships. This thermal expansion temporarily increases atmospheric pressure across the entire planet, creating conditions more favorable for liquid water stability than Mars has experienced in billions of years. The enhanced greenhouse effect begins as atmospheric heating increases the concentration of water vapor through sublimation of polar ice caps and subsurface deposits. Water vapor, a more efficient greenhouse gas than carbon dioxide, amplifies the initial warming through positive feedback mechanisms that extend the duration of the thermal enhancement. Atmospheric circulation patterns change dramatically as temperature gradients drive convection cells with intensities unknown in recorded Martian meteorology. These enhanced circulation systems transport warm air from the heated excavation region toward the planet's polar regions, distributing thermal energy across much greater distances than normal atmospheric processes achieve. The temporary atmospheric thickening approaches pressure levels that allow liquid water to exist stably at Mars's surface for the first time in geological epochs. While these conditions remain far from Earth-like atmospheric pressure, they represent a fundamental shift in the planet's surface chemistry and physics. Sublimation rates at the polar ice caps increase dramatically as enhanced atmospheric circulation carries warmer air toward the planet's frozen poles. This accelerated sublimation adds substantial quantities of both water vapor and carbon dioxide to the atmosphere, further enhancing the greenhouse effect through increased concentrations of radiatively active gases. The thermal effects penetrate into subsurface layers as enhanced atmospheric heat transfer warms the upper meters of Martian regolith. This subsurface warming begins to mobilize frozen water deposits that have remained stable for millions of years, contributing additional water vapor to the temporarily thickened atmosphere. Chemical reaction rates in the heated atmosphere accelerate according to Arrhenius relationships that describe how reaction rates increase exponentially with temperature. Chemical species that normally remain inert begin participating in atmospheric chemistry at rates comparable to those occurring in much thicker planetary atmospheres. The enhanced atmospheric pressure temporarily raises the boiling point of water on Mars's surface, allowing liquid water to remain stable at temperatures well above the normal freezing point. This shift in phase equilibrium creates the possibility for temporary lakes and streams in regions where subsurface ice begins to melt. Convective processes in the heated atmosphere create vertical transport mechanisms that carry surface materials to much higher altitudes than normal Martian weather patterns achieve. This enhanced vertical mixing redistributes chemical species throughout the atmospheric column, creating more homogeneous atmospheric composition. The temporary climate transformation triggers dust storm activity on scales that exceed any natural phenomena in Mars' recorded meteorological history. These global dust storms, driven by enhanced thermal gradients and atmospheric circulation, temporarily obscure much of the planet's surface while contributing to atmospheric heating through solar absorption. Atmospheric chemistry during the thermal enhancement produces trace compounds that have not existed in Mars's atmosphere for billions of years. The combination of higher temperatures, increased pressure, and enhanced mixing creates conditions favorable for chemical reactions impossible under normal Martian atmospheric conditions. The brief warming period allows for erosional processes that operate through liquid water activity. Temporary streams flowing from melting subsurface ice deposits begin carving channels and depositing sediments in patterns reminiscent of Mars' ancient river systems that formed when the planet possessed a thicker, warmer atmosphere. Thermal radiation from the heated surface increases Mars's energy output across all wavelengths, temporarily making the planet a more efficient radiator of thermal energy. This enhanced thermal emission represents a natural cooling mechanism that gradually returns the planet toward its normal thermal equilibrium state. The atmospheric heating creates temperature inversions and thermal stratification that influence how energy propagates through the atmospheric column. These thermal structures create unique optical phenomena as light refraction through the heated atmospheric layers produces unusual visual effects. Atmospheric pressure variations create barometric effects that influence geological processes across the planet's surface. Enhanced atmospheric pressure temporarily increases the efficiency of wind erosion while providing greater atmospheric support for particulate matter suspension. The temporary atmospheric enhancement affects Mars's energy balance by altering both the absorption and emission of solar radiation. The thicker, more dynamic atmosphere absorbs solar energy more efficiently while also increasing the planet's thermal emission back to space. Cloud formation becomes possible in the temporarily humid atmosphere as water vapor concentrations reach levels that support condensation processes. These transient clouds, the first to form in Mars's atmosphere for geological ages, create additional greenhouse effects while also reflecting solar radiation back to space. The enhanced atmospheric dynamics create acoustic propagation conditions different from those normally experienced on Mars. The temporarily thicker atmosphere supports more efficient sound transmission, altering the acoustic environment across the planet's surface. Atmospheric escape processes accelerate as the heated atmosphere expands beyond Mars's normal atmospheric boundaries. The enhanced thermal energy provides atmospheric molecules with sufficient kinetic energy to escape the planet's gravitational field at increased rates. The temporary climate warming affects subsurface permafrost layers by increasing heat conduction into frozen ground deposits. This thermal penetration begins to destabilize permafrost that has remained frozen since Mars's transition to its current cold, dry climate state. Diurnal temperature variations decrease as the enhanced atmospheric heat capacity buffers temperature fluctuations between day and night cycles. The temporarily thicker atmosphere stores and redistributes thermal energy more efficiently, reducing the extreme temperature swings that characterize normal Martian surface conditions. The brief summer conditions create a temporary window for chemical weathering processes that operate through liquid-water interactions with surface minerals. These weathering reactions, dormant for billions of years, briefly resume their role in modifying Mars' surface chemistry. As the thermal enhancement gradually dissipates through radiative cooling and atmospheric escape, Mars begins its slow return to normal climate conditions. The cooling process follows exponential decay relationships as the planet radiates excess thermal energy back to space while atmospheric pressure gradually decreases. The temporary climate transformation demonstrates how external energy input can briefly restore planetary atmospheres to previous evolutionary states. Mars's brief summer offers a glimpse of the planet's ancient climate when thicker atmospheric conditions supported more dynamic weather systems and potentially habitable surface conditions. The gradual cooling marks the end of Mars' temporary return to a more Earth-like atmospheric state. As thermal energy dissipates and atmospheric pressure returns to normal levels, the red planet settles back into the cold, dry equilibrium that has characterized its climate for billions of years, carrying with it the memory of a brief moment when it resembled the warmer world it once was. Imagine humanity's mechanical ambassadors scattered across Mars and orbiting above its surface, suddenly finding themselves transformed from scientific instruments into historians of planetary catastrophe. These robotic explorers, designed to study gradual geological processes and search for traces of ancient life, must now document the complete transformation of an entire world within the span of hours. The Mars Reconnaissance Orbiter, circling the planet at an altitude of 300 kilometers, enjoys the most comprehensive view of the unfolding events. Its high-resolution imaging systems capture the expanding thermal signature as it spreads outward from the excavation site, creating a photographic record of crater formation at unprecedented scales. Surface rovers, including any that might be operating in Mars's northern hemisphere, face immediate existential threats as seismic waves propagate outward from the excavation site. These mobile laboratories, designed to traverse relatively stable terrain, encounter ground motion that exceeds their operational specifications by several orders of magnitude. The European Space Agency's Trace Gas Orbiter finds itself in a unique position to study the rapid atmospheric transformation as its atmospheric monitoring instruments detect chemical changes occurring at rates never before observed on Mars. Spectrometers designed to measure trace constituents suddenly record major atmospheric components shifting in real time. Communication systems linking Earth and Mars face unprecedented challenges as the expanding debris cloud interferes with radio transmissions. The normally reliable data links that connect human operators with their robotic explorers experience dropouts and signal degradation that isolate the mechanical witnesses from their terrestrial controllers. Orbital mechanics become complicated as spacecraft encounter enhanced atmospheric drag from the temporarily thickened Martian atmosphere. Satellites in low Mars orbit find their carefully calculated trajectories disturbed by atmospheric density changes that exceed any conditions encountered during normal operations. The InSight lander's seismometer, if still operational, registers Marsquake readings that saturate its detection capabilities within moments of the initial excavation. This sensitive instrument, designed to detect subtle planetary vibrations, suddenly confronts seismic energy levels comparable to the planet's formation processes. Rovers equipped with weather monitoring stations record atmospheric pressure changes that climb far beyond their measurement ranges. These meteorological instruments, calibrated for Mars's normally stable atmospheric conditions, document the planet's brief atmospheric resurrection through readings that challenge their design specifications. High-gain antennas and solar arrays face mechanical stress from enhanced atmospheric dynamics as temporarily strengthened Martian winds subject spacecraft hardware to loading conditions never anticipated during design phases. These delicate instruments must maintain operational status while experiencing environmental conditions more severe than terrestrial hurricanes. The Perseverance rover's sample collection systems encounter unique opportunities as the excavation exposes deep crustal materials across broad regions of the Martian surface. Rock samples that would normally require deep drilling suddenly become accessible at surface level throughout the crater's extensive ejecta blanket. Orbital imaging systems capture the formation of secondary crater chains as large ejecta blocks complete their ballistic trajectories and impact the surface hundreds of kilometers from the primary excavation. These photographic sequences document crater formation processes that normally remain hidden beneath the surfaces of airless worlds. Thermal imaging instruments record temperature variations across the Martian surface as radiative heating from the excavation site creates regional climate zones with characteristics unlike anything in the planet's recorded meteorological history. These thermal maps document the brief period when Mars experiences temperature gradients comparable to those on more geologically active worlds. Dust monitoring systems detect particle concentrations that exceed measurement capabilities as global dust storms triggered by atmospheric heating create opacity levels that obscure much of the planet's surface. These instruments document atmospheric particulate loading that rivals the most severe dust storm events in Martian observational history. The Mars Sample Return mission components, if already deployed, face the challenge of protecting collected samples while documenting the transformation of their collection sites. These precision instruments must maintain sample integrity while recording geological processes that remake the landscape around their operational areas. Spacecraft power systems experience both opportunities and challenges as the temporarily thickened atmosphere affects solar panel performance, while enhanced atmospheric heating alters thermal management requirements. Solar arrays designed for Mars' normal atmospheric conditions encounter optical and thermal environments outside their operational specifications. Navigation systems confront difficulties as the expanding debris cloud affects GPS equivalent positioning capabilities, while dramatic surface changes eliminate familiar landmarks used for visual navigation. Autonomous navigation algorithms must adapt to a planetary surface that transforms faster than their update cycles. Scientific instruments designed for long-term monitoring suddenly confront the challenge of documenting rapid change that occurs faster than their data acquisition rates. Spectrometers, cameras, and environmental sensors must adapt their operational modes to capture phenomena evolving on timescales measured in minutes rather than sols. Communication relay systems face disruption as atmospheric changes affect radio propagation, while orbital debris creates interference patterns that degrade signal quality. The robust communication networks linking surface assets with orbital platforms encounter environmental conditions that challenge their design resilience. Robotic arms and drilling systems experience unique opportunities to examine freshly excavated materials while confronting operational challenges from enhanced atmospheric dynamics and seismic disturbances. These precision mechanisms must maintain operational accuracy while experiencing environmental conditions that exceed their qualification testing. Data storage systems face the challenge of recording information at rates that exceed their planned data acquisition schedules. Memory banks designed to accumulate scientific observations over months or years must accommodate documentation requirements that spike dramatically during the brief transformation period. Autonomous operational modes become crucial as communication delays with Earth prevent real-time human control during the most critical observation periods. Robotic systems must make independent decisions about prioritizing observations while managing resources during rapidly changing environmental conditions. The mechanical witnesses document not only the immediate transformation, but also the gradual recovery as Mars slowly returns to its normal state. These long-term observations provide insights into how planetary systems respond to and recover from major perturbations. Calibration systems, designed for stable environmental conditions, must adapt to rapid changes in temperature, pressure, and atmospheric composition. Scientific instruments maintain measurement accuracy while operating outside their normal environmental envelopes. Software systems encounter error conditions and environmental parameters outside their programmed ranges, requiring adaptive responses that demonstrate the robustness of autonomous exploration systems. Computer programs written for gradual scientific exploration must accommodate documentation of rapid planetary transformation. The robotic explorers become inadvertent participants in planetary transformation while maintaining their roles as scientific observers. Their documentation provides future researchers with comprehensive records of how technological systems respond to extreme environmental changes while fulfilling their scientific missions. These mechanical historians continue their observations long after the immediate transformation, documenting the planet's gradual return to equilibrium while analyzing samples and environmental changes that will influence Mars research for decades. Their comprehensive documentation transforms a hypothetical catastrophe into a complete scientific data set. The robot witnesses to apocalypse demonstrate the resilience of human engineering while providing unprecedented documentation of planetary transformation. Their observations bridge the gap between theoretical understanding of planetary processes and direct measurement of geological change occurring at speeds that dwarf normal planetary evolution. Time moves differently on worlds recovering from cosmic trauma, where geological healing unfolds across timescales that dwarf human civilization, while atmospheric memory gradually fades back into the cold equilibrium of interplanetary space. Mars begins its journey home to normalcy, carrying within its transformed landscape permanent reminders of the day when cosmic forces briefly awakened a sleeping planet. The cooling process follows exponential decay relationships as Mars radiates excess thermal energy back into the vacuum of space. Stefan Boltzmann law governs this energy loss, with radiative cooling rates proportional to the fourth power of surface temperature differences. The initially white-hot excavation site gradually shifts through incandescent orange, dull red, and finally to merely warm compared to the surrounding Martian surface. Atmospheric pressure begins its gradual decline as the enhanced greenhouse effect weakens and atmospheric gases resume their normal escape processes. The temporarily thickened atmosphere, which briefly supported liquid water stability, slowly returns to the rarefied state that has characterized Mars for billions of years. Water vapor concentrations decrease through multiple pathways as the brief Martian summer draws to a close. Some water molecules escape directly to space as the heated atmosphere expands beyond Mars's gravitational retention capability. Other water vapor condenses into ice crystals that eventually settle back to the surface, rejoining the frozen reservoirs from which they were temporarily liberated. The global dust storms, triggered by atmospheric heating, begin to subside as thermal gradients return to normal levels and atmospheric circulation patterns lose their enhanced intensity. Suspended particulate matter gradually settles according to Stokes's law relationships, with larger particles precipitating first, while the finest dust remains airborne for extended periods. Subsurface ice deposits that briefly melted during the thermal enhancement refreeze as temperatures return to normal ranges. This freeze-thaw cycle creates unique geological textures in the regolith, preserving evidence of the brief period when liquid water existed on Mars's surface for the first time in geological epochs. The enormous crater begins its long evolution from a fresh scar to an integrated component of the Martian landscape. Wind-driven erosion starts immediately, with enhanced atmospheric circulation during the early cooling period accelerating sediment transport into the crater depression. Ejecta blanket modification proceeds through multiple mechanisms as the fine debris scattered across hundreds of thousands of square kilometers gradually redistributes according to local topographic and atmospheric conditions. Wind patterns, influenced by the new crater topography, create preferential transport directions that concentrate ejecta materials in specific depositional environments. Secondary crater chains, carved by large ejecta blocks, begin their own erosional evolution as thermal cycling, wind abrasion, and rare frost formation gradually soften their initially sharp morphological features. These smaller excavations provide natural cross-sections through the ejecta deposits, revealing internal structure and composition variations. The central peak complex within the primary crater starts to equilibrate gravitationally as the rebounded crustal materials adjust to their new stress environment. Gradual subsidence and structural relaxation occur as the uplifted rocks respond to gravitational forces and thermal expansion cycles. Atmospheric chemistry returns toward normal composition as enhanced reaction rates decrease with declining temperatures. Trace compounds produced during the high temperature phase gradually break down or react with surface materials, removing exotic chemical species from the atmospheric inventory. Thermal inertia maps of the Martian surface show the gradual cooling of heated materials as they approach thermal equilibrium with the normal diurnal temperature cycle. The excavation site and surrounding ejecta deposits remain detectably warmer than background temperatures for months after the initial event. Seismic activity triggered by the excavation gradually subsides as stress adjustments propagate through the planetary interior and reach new equilibrium states. Aftershock sequences follow power law decay relationships similar to those observed following major earthquakes on tectonically active planets. The temporary lakes formed by subsurface ice melting begin to freeze as surface temperatures return to normal ranges. These ephemeral bodies of liquid water leave behind dried lake beds and sedimentary deposits that preserve chemical and isotopic signatures of their brief existence. Atmospheric escape rates slowly return to normal levels as the enhanced thermal energy that temporarily accelerated molecular escape velocities dissipates through radiative cooling. the atmosphere gradually contracts back toward its normal density distribution with altitude. Polar ice cap dynamics respond to the changed atmospheric conditions as circulation patterns transport atmospheric moisture toward the polar regions. Enhanced sublimation during the thermal event gradually reverses as normal temperature and pressure conditions return to the polar environments. Cloud formation ceases as water vapor concentrations fall below condensation thresholds, and atmospheric dynamics return to levels insufficient to support significant meteorological phenomena. The brief period of Martian cloud activity ends as the atmosphere settles back into its normally clear state. The gravitational field perturbations created by mass redistribution during excavation begin to relax as post-excavation geological processes gradually redistribute materials according to gravitational potential. However, the fundamental gravitational anomaly created by the excavation will persist for millions of years. Orbital debris populations around Mars slowly dissipate as particles either escape to interplanetary space or return to impact the planetary surface. The temporary debris rings created by suborbital ejecta fragments gradually decay through atmospheric drag and orbital perturbations. Surface pressure variations return to normal patterns as atmospheric mass distribution equilibrates and enhanced circulation patterns subside. Barometric pressure sensors across Mars record the gradual return to the stable, low-pressure conditions that characterize normal Martian meteorology. The enhanced erosion rates triggered by temporary atmospheric thickening decrease as wind speeds and atmospheric density return to background levels. However, the brief period of enhanced erosional activity leaves permanent modifications to surface textures and sediment distribution patterns. Chemical weathering processes, briefly reactivated by liquid water availability, return to dormancy as surface conditions resume their cold, dry characteristics. The chemical alteration products created during the brief aqueous period remain as permanent indicators of temporary environmental change. Thermal emission from the planet gradually returns to normal levels as the enhanced surface temperatures equilibrate with solar input and radiative output. Mars thermal signature, as observed from Earth and other planets, settles back to the baseline established by normal solar heating and internal heat flow. The slow return to silence represents more than just cooling and atmospheric thinning. It embodies the fundamental resilience of planetary systems to maintain long-term equilibrium despite temporary perturbations. Mars demonstrates how worlds can absorb tremendous energy input while eventually returning to stable states determined by their position in the solar system and internal characteristics. As the last traces of enhanced atmospheric activity fade and surface temperatures stabilize at normal levels, Mars completes its recovery from cosmic trauma. The red planet settles into a new equilibrium state that closely resembles its pre-event condition, distinguished primarily by the permanent geographical modifications that will endure long after all atmospheric memory of the event has dissipated. The silence that eventually returns to Mars carries within it the echoes of transformation, a planetary memory encoded in crater morphology, ejecta distribution, and subtle changes to atmospheric composition that will persist as archaeological evidence of the day when a sleeping world briefly awakened to cosmic violence before returning to its ancient dreams of ice and stone. Could the impossible scenario we have explored together reveal truths about our universe that extend far beyond the hypothetical collision between 3I/A Talas and Mars. This thought experiment, grounded in real physics but freed from the constraints of probability, offers profound insights into planetary resilience, cosmic hazards, and humanity's place in a dynamic and occasionally violent cosmos. The excavation event we have imagined demonstrates the fundamental interconnectedness of planetary systems, where single events can propagate effects throughout entire gravitational neighborhoods. The transformation of Mars's atmosphere, the disruption of its satellites, and the creation of interplanetary debris clouds reveal how cosmic events create cascading consequences that extend far beyond their initial impact sites. Planetary defense considerations emerge naturally from our exploration of hypothetical catastrophe, while Mars lacks the biological complexity that makes Earth vulnerable to extinction-level events. The physics governing high-velocity impacts apply universally throughout the solar system. Understanding these processes helps inform strategies for detecting and potentially deflecting objects that might threaten inhabited worlds. The temporary atmospheric resurrection of Mars during our thought experiment illuminates the delicate balance that maintains planetary climate systems. The brief period when Mars resembled its ancient warmer state demonstrates how external energy input can temporarily restore atmospheric conditions, offering insights relevant to both planetary science and potential terraforming technologies. Our imagined transformation reveals the remarkable resilience of planetary systems to absorb tremendous perturbations while eventually returning to equilibrium states, determined by fundamental physical constraints. Mars' gradual recovery from cosmic trauma exemplifies how worlds maintain long-term stability despite experiencing occasional violent interventions. The role of impact events in planetary evolution becomes clear through our detailed examination of excavation processes, atmospheric heating, and long-term geological modification. These mechanisms, operating throughout the solar system's history, have fundamentally shaped the worlds we observe today and continue to influence planetary development. The mechanical witnesses we imagined robotic explorers documenting planetary transformation steps highlight humanity's growing capability to study cosmic phenomena through technological instruments. Our expanding presence throughout the solar system creates opportunities to observe and understand processes that would otherwise remain theoretical. Scientific methodology benefits from thought experiments that push physical understanding to extreme conditions. By examining impossible scenarios through rigorous application of known physics, we test the boundaries of theoretical models and identify areas where additional research might yield new insights. The electromagnetic and gravitational signatures of our imagined excavation demonstrate how cosmic events generate observable consequences across multiple physical phenomena. These signatures, detectable across interplanetary distances, illustrate the interconnected nature of physical processes throughout the cosmos. Risk assessment frameworks gain perspective from considering low probability, high consequence events like our hypothetical collision. While such events remain extremely unlikely, their potential consequences justify ongoing research into planetary defense technologies and impact mitigation strategies. The temporary enhancement of Mars's atmosphere during our scenario provides natural laboratory conditions for studying atmospheric physics under extreme conditions. These enhanced atmospheric states offer insights into atmospheric evolution and the physical processes that govern planetary climate systems. Su Wolvals and Caesartherapeus, vacation of value emerges from exploring scenarios that combine rigorous scientific principles with imaginative premises. Thought experiments, like our Martian collision, help communicate complex planetary science concepts through narrative frameworks that make abstract physics more accessible and engaging. The ejected distribution patterns we examined reveal fundamental relationships between impact energy, planetary gravity, and material properties that apply throughout the solar system. These relationships inform our understanding of how cosmic collisions redistribute matter between planetary bodies. Geological processes accelerated to observable timescales in our scenario demonstrate principles that normally operate over millions of years. The rapid crater formation, seismic propagation, and structural adjustment we described illuminate mechanisms that shape planetary surfaces throughout their evolutionary history. The brief liquid water activity on Mars during our imagined warming period reveals how environmental conditions determine the potential for complex chemistry and possibly biological processes. These insights contribute to understanding habitability criteria for exoplanets and the search for life beyond Earth. Technological resilience, demonstrated by our robotic witnesses, highlights the importance of designing systems capable of operating under extreme and rapidly changing conditions. Space exploration benefits from engineering approaches that anticipate environmental conditions beyond normal operational parameters. The gradual recovery processes we examined illustrate how planetary systems respond to perturbations through multiple timescales, from immediate atmospheric changes to geological adjustments that persist for millions of years. Understanding these temporal relationships helps interpret planetary evolution throughout the cosmos. Observational astronomy gains perspective from considering how cosmic events generate electromagnetic signatures detectable across interplanetary distances. Our scenario demonstrates the rich observational data available when dramatic planetary transformations occur within observable range. The impossibility of tomorrow's collision paradoxically enhances the value of our exploration by removing the practical constraints that limit real-world observations. This freedom allows comprehensive examination of physical processes without the limitations imposed by actual event timing and observational capabilities. International cooperation emerges naturally when considering responses to planetary-scale events, whether real or hypothetical. The global scientific collaboration required to study such phenomena transcends national boundaries and demonstrates the universal nature of scientific inquiry. Future exploration strategies benefit from understanding the complete range of conditions that planetary systems might experience. Knowledge gained from extreme scenarios helps inform mission design and scientific objectives for future Mars exploration and solar system studies. The transformation and recovery of Mars in our thought experiment provide a template for understanding how planets respond to major perturbations throughout the universe. These insights contribute to theories of planetary evolution that extend beyond our solar system to exoplanets orbiting distant stars. As we conclude our journey through an impossible tomorrow, we carry with us enhanced appreciation for the dynamic nature of planetary systems and the powerful forces that continue to shape worlds throughout the cosmos. The catastrophe that will never occur has nonetheless taught us profound truths about the universe we inhabit, reminding us that even in impossibility, scientific imagination combined with rigorous analysis can illuminate the fundamental principles governing planetary existence. Our exploration of tomorrow's impossible catastrophe ultimately reveals that the most valuable insights often emerge not from what happens, but from understanding what could happen under different circumstances. In imagining the transformation of Mars, we have glimpsed the broader principles that govern planetary evolution throughout the universe, carrying forward knowledge that enhances our understanding of worlds, both real and imaginary, both familiar and yet to be discovered.